Hello everyone, I'm Yu Sun from the University of Tokyo. Today I'd like to share with you our recent research on trajectory optimization for an autonomous vehicle driving across stochastic traffic flows based on direct collocation. First, I'm going to present the motivation and the problem of this research. Then I will share with you the method of direct collocation for trajectory optimization. And I will evaluate the scheme's robustness to various traffic flows through the traffic density and speed. Finally, I will conclude the research. To begin, I'd like to share with you the scenario of an autonomous vehicle driving across a traffic flow without collision. The trajectory planning allows to find the optimized path to the desired goal. There have been a lot of researches on the vehicle driving along the road while avoiding obstacles using trajectory optimization. However, research on an autonomous vehicle driving across the road with stochastic traffic flows is insufficient. The trajectory planning helps to find the optimized path to the desired goals with added constraints, such as avoiding collision and consuming the least fuel. The goal of the autonomous vehicles here is driving across the road to the destination without collision with other moving vehicles on the road. At the same time, minimize the overall fuel consumption during the course. This leads me to my next point, the problem definition of the scenario. It's a nonconvex trajectory optimization with additional constraints. In this research, the x-xis locations of all vehicles on the road are randomly initialized, and a deterministic interval is kept between every two vehicles on the same line. All vehicles on the road are with constant velocity, and the input trajectory and the state trajectory is represented explicitly as the piecewise polynomial functions. At last, the constraints of the max speed limit and the max torque limit are employed. Moving on to the next point, I'd like to present you the method of direct collocation for trajectory optimization. First, we analyze the dynamics of vehicles on the road, the dynamics of the autonomous vehicles and the other moving vehicles on the road, which can be broken down into horizontal dynamics and the vertical dynamics shown below. Then the piecewise polynomial functions were used to represent explicitly both the input and the state trajectory. I'd like to bring your attention to this graph. The note points here were used for decision variables for optimization, which were obtained with a certain interval of 0.5 seconds from the start point to the end point. The torque UT employed a first-order polynomial, which means any value between tk and tk plus 1 can be computed from utk and utk plus 1. And the dynamics xt employed a cubic polynomial functions, which means any value between tk and tk plus 1 can be defined by xtk, xk's first order, and xtk plus 1 and xk plus 1 first order. On the other hand, the collocation points were used for their added constraints to the derivative of the spline for optimization. We computed the dynamics of the autonomous vehicles at this collection point using Taylor series about xtk. The constraints employed include no collision with other vehicles, complete the task with a minimum torque and consumption, and the maximum speed limit, maximum torque limit. And its dynamics representation is shown on the right side. Then we adopted a solver for computing the optimized pathfinding result based on the defined dynamics of systems and these constraints. An initial guise of the trajectories was used for faster computation, where a direct line connecting the start point and the end point employed as the states and the talks during the whole course stayed at 0. Now let's take a look at the evaluation result. We evaluate the robustness of the scheme to various traffic flow rates, which are controlled by the traffic density and the traffic speed. First, we studied the traffic density's influence on the pathfinding result. We use the number of all vehicles on the same line to represent the traffic density. For instance, a traffic density of 1 means 1 moving vehicle driving on each line, thus 4 vehicles on the road in total. From left to right, there are traffic flows with the traffic density of 1, 2, 4, and 6, respectively. The graph on the first line shows the initial position of stochastic moving vehicles on the road. The second line shows the pathfinding results of the scheme, where the red line represents the initial guess and the black lines show the optimized trajectory for the autonomous vehicle. The third line illustrates the change in the autonomous vehicle's velocity and the torque during the course, where we use a normalized representation of these variables with respect to the maximum limit. Then we studied the influence of moving vehicles' driving speed. The speed unit here is the meter per second. Also, we consider scenarios vehicles driving on each line of the road with a traffic density of 2. We set the speed of vehicles on the inner lines larger than the ones on the outer lines for exploring a more diverse scenario. From left to right, a traffic flow with a traffic speed of 3 meters per second, 4 meters per second, 6 meters per second, and 8 meters per second for vehicles on the outer lines, and 4, 5, 7, and 9 meters per second for vehicles on the inner lines. The results of pathfinding with these various traffic speeds are shown below. At last, we visualized the change in the autonomous vehicle's dynamics, covering the horizontal positions with respect to the horizontal velocity and the vertical position with respect to the vertical velocity when different traffic flow rates adopted. As a result, the increase of the traffic density and the traffic speed brings more possibility that the autonomous vehicle takes sharp steering during the course. When the increase in these two factors arrives at a great extent, it has been showing no feasible solutions for driving across the road without collision. To summarize, we presented the optimization problem of an autonomous vehicle driving across traffic flows with various traffic densities and traffic speed. Several constraints were added to the systems, including collision avoidance, maximum speed limit, maximum torque limit, and the minimum fuel consumption. Then various traffic flow rates were used to evaluate the scheme, the results of which show the great robustness of the scheme to stochastic traffic flows. And for future work, a comparison with other approaches such as RRT star, rapidly exploring random tree star, is to be conducted for the trajectory optimization problem. And that brings us to the end. I'd like to thank you for your time and attention today. I would be happy to answer any questions you may have now.